I think we can gradually start. Welcome everyone to Quantum Matter in Math Physics Harvard CMSA seminar. We are delighted to invite João Caetano from CERN, and he has done various interesting work. Today he will be speaking about Unorientable Quantum Field Theories from crosscaps to holography. Just remind the audience, please feel free to ask questions and interact with João during his talk. And so please go ahead. João, is all yours. Thank you.
Thank you very much. Big thanks, Jovan, for this very kind invitation to speak at this seminar. So today I'm going to talk about unorientable quantum field theories, by which I mean quantum field theories that are defined in unorientable manifolds, like this one here in the picture, which represents the real projective space in 2 dimensions, or RP2. And this subject has been studied from various perspectives and very well studied. But today I'm going to talk about some specific features that perhaps were less explored, namely the connection to integrable models and also holography, or more generally ADS-CFT. Okay, so perhaps one of the first instances where we encounter an example of an unorientable quantum field theory in 2 dimensions is when we study the worldsheet theory of unoriented strings. And unoriented string theory is, of course, relevant in many situations. For example, famously, massless unoriented open strings correspond to SON or SPN gauge bosons. Okay, so this is a well-known fact. And this fact has a later incarnation also in holography, when we try to study gauge theories based on the gauge group SON or SPN, that typically is the holographic dual involves unoriented strings. So related to this are also other objects in string theory called manifolds, which gauge precisely the worldsheet parity of the string and give rise to unoriented strings. And of course, these manifolds are objects that are used in various contexts in string theory.
By the way, João, I think the slides are not changing though.
Oh, it's not changing?
It's just on the front page.
Oh, okay.
Full screen.
Is it changing now?
No. Maybe try full screen.
Yes. And now? It's not changing?
No.
Okay, perhaps let me try to, I apologize. Maybe I can try to share the PDF. I don't know if that makes a difference. Or maybe let me just try to stop sharing and sharing again.
Actually, it just work. You start to change when you start.
Oh, okay.
Okay.
How about now? Is it changing?
It's right now it's on the front page.
Yeah, okay. So there's a problem then. Maybe I can try.
How about full screen? I think
okay.
you are not using full screen for sharing the slide. It's like a there's a right now it's right now it's great.
And it's
works
changing.
Fine. Yes, works fine. Great.
Perfect. Okay, I apologize. As I was saying, there's this fact that massless unoriented open strings correspond to SON or SPN gauge bosons, which is a fact that appears later when we study holography. And I was also mentioning that there are some objects in string theory called manifolds, which precisely gauge worldsheet parity. And by gauging the worldsheet parity of the string, it gives rise to unoriented strings. And these objects are used in many contexts, in particular in string compactifications, and also attempts of constructing de Sitter solutions in string theory. Okay, so let's first talk about unorientable QFTs in 2 dimensions. And in 2D, the way to construct unorientable manifolds, where we're going to place the QFT, is by adding crosscaps. So a crosscap is the manifold that you obtain when you start with the complex plane and you make this identification. Z is identified with -1 over Z bar. So if you look at this gray area here, which represents the complex plane, so I have a unit circle, and points outside the unit circle will be identified with points inside the unit circle. And in particular, at the boundary, you identify points at antipodal locations. Okay, so this is the manifold you get upon doing this identification. Now we put a quantum field theory in this geometry, and we imagine doing some radial quantization, for example. And this defines what's called a crosscap state. This weird boundary condition defines what's called a crosscap state. Okay.
Just make sure the terminology is a crosscap the same as S2 Z2, which is RP2.
Yeah. So if you start with a sphere and you add a crosscap, then you get RP2.
Okay. Thanks.
Okay. So from this picture, it's clear that the crosscap states have some analogies with boundary states. It's just that the boundary conditions at the boundary of this disk are a little bit weird in the case of the crosscaps. And of course, boundary states in 2 dimensions, of course, are tremendously important in physics, and they typically are studied in 2 ways. Many ways, but essentially most typically in 2 ways. One is to look at the fixed points of RG flow and then apply CFT techniques at those fixed points. So this is famously started with Ishibashi, Cardi, and then there's thousands of works on this. And upon having these specific boundary conditions, then we can construct boundary states for specific CFTs like minimal models, etc. And the other approach, which also is very popular, is to look at integrable models, which are models that have infinitely many conserved charges. Okay. And for these models, there are some special types of boundaries, which are called integrable boundaries, that preserve an infinite subset of these conserved charges. Okay. And in those cases, one can actually go away from the fixed points and study the massive phase of the theory. So this has been introduced by Zamolodchikov and Goshal, and it's a very important part of the study of integrability. Now, for the crosscap states, the situation is a little bit different. So they have been studied in CFTs already from the early work of Ishibashi, and in many circumstances also in string theory. But as far as we could tell, they've never been studied in the context of integrable models. Okay, so this was in 2 dimensions. Let's go to 4 dimensions. So in 4 dimensions, what you might call the analog of the crosscap in 4D is RP4 instead of RP2. So RP4, I define just from a sphere, a 4-sphere with the antipodal points identified. So I mod out by this identification. So this might be the simplest unorientable 4 manifold. And importantly, this is a locally conformally flat manifold, but not globally. And this fact is interesting. First, it shows that this is like a genuine curved space, not just a Weyl transformation of flat space. But at the same time, the fact that it's locally conformally flat, it's interesting because then if you imagine putting a CFT in this geometry, in the UV, the theory will remain the same. So the OP structure of the theory will be still controlled by the same conformal dimensions and structure constants as the theory in flat space. Okay, so this fact here that the theory is locally conformally flat will play a crucial role throughout the talk. Okay, right. So the outline for the talk and at the same time the outcomes are the following. So in the first part, I will describe integrable models in 2 dimensions and define crosscap states. And the punchline here will be that if you start with an integrable model in flat space and you go to the crosscap manifold, then integrability will be preserved. Okay, in other words, crosscap states preserve integrability. So, and then I will explore some consequences of this. And then in the remaining part of the talk, I will go to 4 dimensions and study what's perhaps the simplest field theory in 4 dimensions, which is n equal to 4 supersymmetric Yang-Mills, maximally supersymmetric Yang-Mills theory in 4 dimensions. And I will place it in RP4, this manifold that I just described. And there are several ways of placing this theory in RP4, depending on whether, or at least 2 ways, depending on whether we gauge the charge conjugation. And I will explain in detail what do I mean by this. And I will show that in this case, the theory remains integrable in the planar limit. Okay, so it's a known fact that n equal 4 is integrable in flat space in the planar limit. So it will remain, there will be some integrable structure underlying the theory in the planar limit. But there's also the option where we do not gauge the charge conjugation. And in that case, we don't get an integrable theory in the planar limit, but one can still study by holography, supersymmetric localization, and even a conformal bootstrap. But I will emphasize more the holography part. Okay, so that's roughly the plan for the talk. Please, as Jovan said, please feel free to interrupt me, and I will pause to see if there's any questions so far.
Maybe let me ask one. Could you say a few words about integrable boundaries and algebraic flow that you say done by Zamolodchikov? Maybe just say in what context do you need this technique? I think you just mentioned in one sentence.
Yeah. So well, for example, you can well, there are several contexts where you can take advantage of the fact that boundary might preserve the integrability. For example, you can follow, for example, analytically the behavior of the G function along the RG flow, for example. That's one thing. And you know, you can study the theory away from the CFT point, and you know, I mean, there's a lot of contexts where this also plays an important role. For example, in string theory, you might consider, so the boundary in string theory amounts to some D-brane. So sometimes you're lucky that if you start with world sheet theory that is integrable and you add some D-brane, then integrability is preserved. And in those cases, you can study and you can actually construct exactly the boundary state, okay? Even away from the CFT. So in the case of integrable boundaries, you can construct explicitly the boundary state.
So let me just mention what's the boundary here and what's integrable boundary. So for the case of a crosscap state, when you refer to the boundary, what's the dimensionality of that state?
Yeah, so in the case of crosscap state, there's really no boundary, because if you define a quantum field theory in this geometry, you just impose some sort of periodic boundary condition. So there's no degrees of freedom, additional degrees of freedom, like in the case of a boundary. So in the case of a boundary, you have to specify the boundary conditions at the boundary. So there's like a one less dimensional surface with some degrees of freedom that live on that surface, or in that submanifold, let's say. But here there is no such a thing. There's no boundary.
But when you say integrable boundary, what are the boundary you are specified? Do you cut out maybe a disk out of this?
Yeah. So in the case of a boundary, indeed, you cut out a disk, and then the statement that these special boundaries preserve integrability is that if you, for example, scatter some particle off this boundary, there are some special properties, like, for example, there's no the number of excitation is preserved, the bulk factorizability of the scattering is preserved, so that it's not always the case. It's a very special circumstance where you can add a boundary and the bulk properties, nice properties of integrability are preserved by the boundary. So even if you start with some free field theory, which is obviously integrable, and you add an arbitrary boundary, integrability is not necessarily preserved.
So I just maybe be concrete. So, for example, would you be studying a state living on boundary of a Mobius strip? Is that something you are saying? I suppose the RP2 cutout disk give you Mobius strip. So when you say the integrable boundary, do you define a boundary condition on such a Mobius strip?
Well, the Mobius strip involves both disk. You cut out the disk, but also involves a crosscap, right? It's like a cylinder where on one hand you have a disk and the other hand you have a crosscap. But in my talk, I will not talk about boundaries. I will just talk about crosscaps. So I will specify for the Klein bottle, not the Mobius strip. Okay. In what follows.
So would you discuss integrable boundary at all? Maybe later in your talk, because you mentioned
no. Okay. No, unfortunately, I could give a talk on that, but that was not my plan. Okay. But I can say throughout the talk, I can point out some similarities and differences with the boundary.
So what exactly is integrable boundary? I'm not sure I follow.
So there are two ways of thinking about it. So in quantum field theory, you can either think of the boundaries in space or boundaries in time, which are related, of course, because you can change space and time. So the statement of integrability is that, for example, let's think of a boundary in time. Okay, so I start evolving the system starting from a boundary. The statement of integrability is that this state that you start with is annihilated by infinitely many charges. Okay, it might not be infinitely many. So the original theory has infinitely many, then you pick an infinite subset. And this state that you start with, it's annihilated by this infinite subset. That's the definition of integrability.
An integrable boundary means
what I just said. So that's
integrability, but integrable boundary is
it's a certain state. You can also take the point of view of rotating, exchanging space and time, and this what to do is that you start with some quantum field theory that's integrable, and then you add a term in the, let's say, Lagrangian or Hamiltonian that is restricted to some slice in space, yeah. So that's what I mean.
Yeah, please go on. Thanks.
Okay. So yeah, I should mention that this is about a series of works with some collaborators. So this was done with my colleague here at CERN, Shota Komatsu. Then there is some work that we're going to try to wrap soon with Shota Komatsu, Leonardo Rastelli, and Paolo Soresina. And finally, this was some work that I did with Leonardo earlier this year. Okay, so maybe this will clarify some of your questions. So let's start with crosscaps in 2 dimensions. So essentially, the goal will be to construct explicitly this crosscap. So this is what I denote by this C here. So that's a state that I overlap with some bulk state. And I want to compute this overlap for any arbitrary bulk state. So in this way, I define completely the crosscap state. So the idea is to adopt some of the strategies that we use in conformal field theory. So we're going to start with the Klein-Bottle partition function into distinct channels. So this is a Klein-Bottle. So that's a cylinder where you have a crosscap on one hand and another crosscap in the other hand. And we can choose two channels depending on how we assign space and time. So let's take the so-called tree channel or closed string channel, where I assign time in this direction and space in this direction. So I have like a closed string propagating from one crosscap to the other. And it's immediate to construct a partition function. So I just sum over states that are quantized on this circle here of size L. Then I evolved along the time for a time R, which is the length of the cylinder. And then I have to take into account the overlap between the crosscap state and the bulk state here. So now I take the large R limit, and this, as usual, projects me down to the ground state. Okay. So this is simple. Now I can move to the open string channel, and here the situation is slightly different. So first of all, time and space are now identified in the orthogonal directions. So now time is this circle here, and space is along this direction. So the first thing that we should notice is that, in fact, due to this crosscap identification, the Hilbert space is defined on a circle of size 2R. So because of this identification, I have a circle of size 2R. So now I start with the state here at the bottom. I evolve it by time equal to L/2. I get to the state in the top. But because of the crosscap identification, the orientation is reversed. Okay. So in other words, the partition function in this open string channel will be just the Hamiltonian evolution over a time equal to L/2. And then parity operator is the operator that reverses the orientation. Okay. So, and then I take a trace over an Hilbert space of size 2R. And so I can decompose this into energy eigenstates as usual, and finally into parity eigenstates. So at the end of the day, I get that this partition function is just a sum over states weighted by some parity eigenvalues. I can take the values plus or minus 1. Okay. So now, as usual, we equate these two channels. And then if I take the large volume limit, I can see that the partition function, so on one hand, I have this partition function, which will be equal in the large volume limit to this overlap with the ground state. So in other words, this overlap of the crosscap state with the ground state in the bulk controls the density of states weighted by the parity epsilon. So let's be a little bit more precise about this. So I can define as usual the free energy, which will be some parity weighted free energy. And using the expression before, I have an extensive piece, which scales like the energy of the ground state. And then I have other one piece, which is this overlap between the crosscap state and the ground state. So if you're vaguely familiar with the story of a system with boundaries, this has exactly the same structure as a thermal free energy of a system with boundaries. And in that case, there's also some extensive piece, which is exactly the same as here. And there's also another one piece, which is called the boundary entropy or GG function. Okay. So here we don't have a boundary entropy. We might call this something like crosscap entropy, but that's also another one piece. Okay. Now, this is perfectly general. You can define this overlap for any quantum field theory. But integrable models are nice because in integrable models, we know how to compute large volume partition functions. Okay. there is a technique called thermodynamic Bethe-Ansatz that allows us to compute by saddle point large volume partition function. And also, we can also get to order 1 fluctuation, which is what we are after. Okay, so let me, I will not go into the details of this derivation of the thermodynamic Bethe-Ansatz. It's a subject on its own, but I will just emphasize some aspects of it. So the first thing is that we usually use thermal partition functions, but here we have this parity operator that we have to learn how to deal with. That's the only subtlety here. So let's see. So let's do this for the simplest possible integrable model. So let's imagine that we have just a single type of massive particle. So the prototype of integrable model into D is this Sinch-Gordon model. So we imagine that we have a bunch of particles in a large ring. So that's typically in integrability, that's the language that we like to use, is that we have like a large circle with a bunch of particles labeled by momenta. And the states, the energies, eigenstates are labeled by the momenta of these particles. And because they are in a ring, in a periodic ring, we have to quantize this momenta, and this is what's called the Bethe equations. So P here will be quantized by this equation, and S here is the two-body S matrix. And that's all that matters. Because the feature of integrable models is that the scattering always factorizes into two-body scattering. Okay, and if we use the standard eigenstates, which are also called beta states, we have that the parity acts on them just by flipping the momenta of the individual particles. Okay, so this is the setup that we're going to consider. Now, if I expand now this, what I get is that this parity, the insertion of this parity operator will project me onto states which are parity invariant. And the states which are parity invariant are the ones that satisfy this constraint, is that the set of the momenta of the individual particle is invariant under individual flipping. Okay, so when we get to this point, then we just have a standard thermal sum without parity being inserted, and so we can apply the standard techniques of the thermodynamic Bethe-Ansatz to compute the saddle point and the fluctuation. Let me just mention that this selection rule here that we have, that this set of individual momenta is invariant, is associated precisely to the fact that this setup is preserves infinitely many conserved charges. Okay, so we can apply thermodynamic Bethe-Ansatz now, and let me just be a little bit more specific about it. So we have to compute this sum, where we have to sum over all states that satisfy this constraint. Okay, so now remember that we are now in a circle of size 2r. Okay, so the only sets that satisfy this equation are, of course, the sets where you have all the sets of momenta and then the flipped ones. So this is clearly invariant under p goes to minus p. And you can also add a zero momentum particle. Okay, so the periodic boundary conditions in one case and the other, which I call S and T sector. So the S sector stands for the sector where I just have this bunch of particles, and the T sector is the one where I include a zero momentum particle. The Bethe equations look like this. Okay, in one case I have a product of S matrices with this additional term, and in the other case I have the same as before, but with just a scattering matrix involving the zero momentum particle. Now, when we look at this system, it formally, okay, so yeah, then of course this sum here is a sum over S and T sector. So when you look at these equations, this formally looks like a system with boundaries, two identical boundaries, okay? Where for a system with identical boundaries, the Bethe equations that I write is just a periodic or just a condition that if I start with a particle and go around the world, reflect at the boundaries and come back to the same point, I should get back to the same point. So this is the type of equations that I write for a system with open boundaries, where here R is this reflection amplitude. Now, formally, for the crosscap, I have some equations that look like this one for the boundary system, except that now what plays the role of the reflection factor is this S matrix here. Okay, so in other words, I can just use the very well-known results for boundary overlaps, where I just replace the reflection amplitude by these other factors. And okay, this might be a little technical, but bear with me. And this is perhaps one of the last technical slides. So let's see what happens with the boundary entropy. So for the boundary entropy, instead of considering a Klein bottle, I just consider a finite cylinder with two boundaries at these yellow circles. So in that case, the partition function in the closed string channel will, in the large volume, will be again dominated by this ground state energy. And the other one fluctuation is the overlap between the boundary state and the ground state of the theory. And people in integrability managed to compute this overlap. Here I show the result for a single particle with diagonal scattering in no-bound states. So that's the simplest integrable model. And people found this result by studying the one-loop fluctuation around the saddle point. So the one-loop fluctuation is precisely in the origin of these determinants. This is roughly the one-loop determinant that you get. So this formula here, let me break into parts. Looks a little bit strange, but let me go step by step. So it involves the y function here, this y function, which is nothing but the solution of the saddle point equation. Okay, so this is also called TBA or thermodynamic Bethe-Ansatz equation. So it's an integral equation, integral because of this star here, which represents a convolution. So it's a nonlinear integral equation that involves the dispersion relation of the model. So that's the relation between the energy and the momenta, and the moment is parameterized here by U. And there is this kernel here that involves the two-body S matrix of the model. Okay. So that's one ingredient that appears here, the y function. Now there's these determinants here that are in fact Fredholm determinants that involve the y function itself and also the kernel that I just wrote here that involves the two-body S matrix of the model. And also there is this prefactor here, which in the case of the boundary depends on this reflection amplitude plus some additional terms. Okay, so for the case of the boundary, all you have to give to this formula is the S matrix of the model, and also the reflection amplitude, which is specified by which type of boundary you're inserting. So now the claim is that for the crosscap overlap, we just recycle this formula and we replace the reflection amplitude by these other two factors that I showed before. Okay, so that's easy. And what we get is something that formally looks like the simplest possible G function. So there's no dependence on reflection amplitude anymore because there's no reflection. And this is what you get. You get a ratio of determinants times this factor here, which has two contributions, 1 and this square root, which comes from the S sector and T sector. And also it depends on the y function, which is the solution of the saddle point equation. Okay. So this is one of the results that we achieved. Let me say a few more things about it. So I just showed you the overlap between the crosscap and ground state. But in fact, we can extend this to any excited state just by some sort of analytic continuation of this formula. And what we get is an expression that looks very much similar to the previous one, except now that these kernels are modified in this way. Looks a little bit complicated, but this use here is a sum over beta roots. And these beta roots, which are solutions of the beta equations, are what specifies which excited state you're considering. Okay, so that's one observation. And the other observation is that we can also simplify our lives by taking a large volume limit, so take L to be very large. And in that case, this formula collapses to this simple ratio of now usual determinants given by this expression here that involves the kernels that I showed you before. Okay. So this is sort of like what we've been able to achieve at this point. It's now, of course, since you know the crosscap state for any excited state, so then you define the crosscap state exactly. Okay. So,
excuse me, naive question. So how does this formula or the evaluation depends on what the field theory you are consider or what theory you are consider? Are there input? For example, if it's a CFT, does it depend on the CFT?
Right. So all the input is in the S matrix, the two-body S matrix of the model. So if you give me some integrable field theory and you know the S matrix, then that's all it takes. So there's no dependence on anything else. So if your model is specified by some S matrix, for example, for the Sinch-Gordon, we know the non-perturbative S matrix by earlier works of Samolochikov and many other people. So in that case, we can just input in this formula the S matrix, and that spits out the crosscap overlap.
And this will affect which variable here, like 1 over 0? And the
sorry.
I say that those S matrix are input into Y0, Y of 0 or G hat? Dependence, make sure.
Right. So there are several places where the S matrix appears. One is that this Y appears into places in this Y0, Y evaluated at 0, but also it appears in these kernels here, 1 over Y of V, and it's being integrated. And so the way it works is like a two-layered system. So you solve first the Y function. And to solve the TBA equation, of course, you need the input of the S matrix of the model. So you solve the Y function, and then once you have the Y function, you inject into this formula, and you get the crosscap overlap. And so the S matrix appears as inside the Y function, because the Y function is the solution of the TBA that involves the S matrix, but also in this kernel here. So it's a little not very easy to evaluate, especially because you have here Fredholm determinants. It's a different question how to evaluate this efficiently. In most of the cases, you can only do it numerically. Also, because to solve the thermodynamic Bethe-Ansatz equation, you need most of the time to do numerics. But for example, there's this asymptotic limit where things are easier to compute. And you can explicitly compute these determinants as a, it's a finite dimensional matrix that you can compute.
Okay, thanks. Are there some concrete examples that using crosscaps that you can distinguish something that you cannot on other usual orientable setup? Will you give some example? The quantity that you...
I think there is one example that might be interesting for that. Yeah, it's coming now.
All right, thanks.
Okay. So right, so we get this overlap, and of course, I mean, the point is not just to compute the overlap just for the sake of having an exact result, but rather perhaps you can study, try to study this quantity and try to, get some universal information about the nature of these crosscaps. So one thing that we would like to do now is to then study this quantity log of this overlap, which is very much like the G function. So the G function would be the overlap between the overlap and the ground state. Now we have something which is analog of the G function. Okay, so we'd like, first of all, to check whether this expression is correct, and maybe to try to, for example, study how this quantity evolves under the RG. Of course, the inspiration is that the G function has this nice property that it's monotonically decreasing from the UV to the IR, and it's very natural to ask whether this quantity, this boundary entropy, also has the same type of behavior. So, so let's see. So the goal, again, is to check this result and study how crosscap entropy evolves under the RG in a few examples. So the example that I'm going to focus today is the so-called staircase model of Zamolodchikov. Then let me explain what is this model. So this is an interesting model that has been studied quite a lot because it's very easy to, for example, study RG flows of several quantities. So how does this model is defined? So the idea is to start with the Singe-Gordon model, which I already mentioned, which is an integrable model defined by this Lagrangian. Okay, so describes one type of massive particles with mass m. There's here the coupling B. So this is how we define this model. And it was possible to find the exact S matrix of this model. Okay, exact in the coupling B. And it's given by this. It's given by this expression where this gamma here, it's related to the coupling constant by this relation. And this defines completely the model, okay? And it's all it takes because the model is integrable, so all you care is the two-body S matrix. And here, U and V, you should think of it as a parameterization of the moment of the incoming particles. Now, there's this coupling here, gamma, which is has a funny property, which is invariant under gamma goes to pi minus gamma. And this is the statement of the weak-strong coupling duality of the model, very much like in the Liouville. And the proposal of Zamolodchikov was to say that, well, let's look at the self-dual point, which is at pi gamma equal to pi over 2, and analytically continue this coupling in the imaginary direction. Okay, so the sign plus and minus are not important, the distinction. So let's take this analytic continuation. So if you do that, you get some S matrix, which is still physical in the sense that it satisfies the properties that we usually like on S matrix. It's real analytic, it's unitary, it's crossing symmetric. Although the Lagrangian description is not so clear because we are complexifying the coupling. So it's not clear what happens at the level of the Lagrangian. But we take the point of view that the model, this resulting model, is defined by this S matrix. Okay. Now, the interesting thing about this model happens when you take this theta 0, this parameter here, to be very large. So let's do that. Let's take this parameter theta 0 to infinity and compute the effective central charge, or in other words, the ground state energy. So this effective central charge, maybe it's not so familiar for people not doing integrability, but it's some quantity that approaches the central charge whenever the model hits a fixed point. Okay, so it's a quantity that depends on the massive parameters of the theory, but as it goes close to some CFT, this effective central charge tends to the value of the central charge of the CFT. So, when you compute this effective central charge for this model in the limit where theta 0 is very large, and you compute it as a function of the volume of the system, you get this funny behavior. You get something that looks very much like a staircase. And the idea is that as you change L, you are effectively turning on some relevant deformation of the model, and you are inducing some RG flow. And what's interesting is that these plateaus of this effective central charge, they coincide precisely with the central charges of the A-series minimal models. Okay. And so the interpretation of this staircase model is that it's some parametric family of quantum field theories, of massive quantum field theories, parameterized by this theta 0, that whose RG interpolates between all these A-series minimal models. And of course, these transitions between the minimal models, they are very well known. They are the ones induced by the least relevant operator, phi-13, which is actually present in all of the A-series minimal models. Okay. Now, let me just mention that this staircase behavior is more pronounced as theta is larger. The larger theta is, the more pronounced are these staircase. And that's why it's called a staircase model. Okay, so this is an excellent toy model to study RG flows. For example, we now might want to compute this crosscap entropy and see how does it behave. Okay, so so we can ask what is the behavior of this log of this overlap for the staircase model. And this is what we got. So P here, it's what I called this overlap. So we call this P function instead of G function, just give it a name. And what we observe is that it has this behavior. It's like a quantity that also goes through several plateaus. And in this particular case, is monotonically decreasing. Okay. Now these plateaus, of course, we can compute from CFT, because we know that this corresponds to A-series minimal models, and this cross-cap overlap can be computed in the CFT just by using this expression that takes into consideration it's a sum over irreducible representations of the various order algebra. It involves the modular S matrix between this representation and the identity, and then it takes also into account the degeneracy of states. And the chiral and anti-chiral part are identified because of parity. So this is a very general formula for cross-cap overlap in CFT. And then when we specify for the A-series, we get precisely these values here, which is precisely the values of these plateaus. So this is kind of a check of this formula. So it matches the CFT expectations, but also it suggests something that you might suspect, that maybe this quantity is actually monotonically decreasing, like the G function. Okay, so we were thinking that this could maybe was the case. But then we decided to study this quantity in different models. And we generalized the story of the staircase minimal models to the D-series minimal models, which are non-diagonal. Okay, so let me just remind what D-series minimal models are. So as we have seen, so there's these A-series minimal models which are the minimal models that we first encounter. They all contain some Z2 global symmetry. And the D-series is obtained by gauging this Z2. So sometimes it's called the Z2 orbifold of the A-series. Now, this is, as it's well known, it's non-diagonal and also contains an emergent Z2. And what gauging in practice means, it's the standard think of orbifolds. So we add some twisted sector for which we consider fields that are periodic up to the action of the Z2. And then we restrict the Hilbert space to Z2 invariant states. So that's what it means to gauge this Z2. We can mimic these two steps at the level of the Bethe ansatz. Okay. So adding a twisted sector is to consider particles that are antiperiodic in this large circle or large ring that I considered before. So instead of considering periodic boundary conditions, I add a -1 here, which means that at the end of when you go around the world and you come back to the same point, you have to act with the Z2 symmetry, which is this -1 here. And then restricting to Hilbert space to Z2 invariant states amounts to consider states with even number of particles. Okay, so that's the Bethe ansatz counterpart of this gauging. And so we can redo the thermodynamic Bethe ansatz analysis that I just talked about, having this Bethe ansatz as a starting point. Okay, so what we get is a similar expression to what we found before, except that now the prefactor is a little bit different. So the claim is that now this overlap here computes the crosscap entropy for the D-series minimal models. And so it's very interesting to see what happens and try to plot this as a function of the relevant coupling or the volume of the system. So when you do that, you also get something that goes through some plateaus, and it seems that it decreases, except at the deep IR, where it goes to a value which is 1/2 log of 2. So in contrast with the A series, it's actually not monotonically decreasing because it increases in the deep IR. So it's, of course, very simple to interpret what happens is that in the case of the A-series minimal models, it's known that you, in the deep IR, flow to some massive phase, whereas in the orbifolded case, you flow to some phase where this Z2 symmetry is spontaneously broken. And so you have actually two vacua. And that's why we get this factor of 2. Okay. So, what's the conclusion of this? Well, first of all, along the D series, strictly speaking, the P function is monotonically decreasing because only up to these steps, these plateaus, this corresponds like to the Ising model, tri-critical Ising model, 3-bots model, and up to there, the models are all non-diagonal and then they become diagonal. So up to here, the function is monotonically decreasing. But in general, it increases in this symmetry breaking phase. Okay, so the conclusion is that it's not true that this crosscap entropy is monotonically decreasing, but it would be interesting to understand if there is some connection with the increase of the P function or this crosscap entropy and some symmetry breaking phase. And so we didn't explore this further, but answering to Joven's question, so maybe maybe this crosscap entropy is useful for something. Maybe there is some connection with some symmetry breaking phase, or maybe it's a test of some symmetry breaking patterns of the theory. But it's something that might be worth exploring further. But the punchline is that generally this is not a monotonically decreasing function. So it would be interesting also to know under what circumstances this is monotonically decreasing, but perhaps it's not true in general. Okay. So are there any questions at this point? Okay.
Actually, are there some specific theory that you are consider, like given maybe a number of primaries and given some S matrix? I think probably you have some general statement of formulation, but are there some particular examples you are looking at, or you can compare? Maybe this is not what you plan to do, but I just asked in case you have something in mind.
Not really. I mean, the only actual computation was for this staircase model. But of course, we can, I mean, in principle, you could try to generalize this for more complicated theories that have different types of particles. They have non-diagonal scattering. And if you generalize these expressions in that context, there's, of course, a wider class of models that one can study. But we are not thinking about that right now. We are not trying to, maybe in the future we will, but at the moment we're not trying to push this further.
Okay.
Okay.
So, by the way, is a theory you consider here also allows fermions require a spin structure, that type of theory? Do you consider those spin structures in the theory?
Yeah, we have some comments about that in the paper. We try to generalize for fermionic minimal models, like to have some model that interpolates between the fermionic minimal models. But so I think the answer is yes, it's possible to generalize. We made some comments on that in the paper, but yeah, we didn't try to push this further. At the level of integrability, going from fermionic models or bosonic models is very simple. So at the level of this matrix, that's usually amounts to have an overall sign in front of the S matrix. That innocent looking change turns the model into a fermionic model. And that's what we managed to do. Just if you start with this staircase model and you reflect the S matrix, send S matrix to minus itself, it seems that you interpolate between some fermionic minimal models as you tune the volume of the system. But that was sort of preliminary and not. It's not entirely obvious how it works in practice, but the answer is yes. I think one can generalize this for including some spin structure.
Okay, thanks. By the way, if ever there are some specific examples you can mention, that will be really helpful for, I think, the general audience.
Okay.
I don't know, but don't worry if there's not. But if you come up with,
okay, maybe in the end I can say a little bit more.
No problem. Thank you very much.
Sure. Okay. So great. Okay. So I have. I guess I have like half an hour or something. How am I doing with time?
Yes.
Okay.
Yes.
So let me just quickly flash over the spin chains. I don't want to spend too much time with this, but let me just be very quick about this. So we can also generalize this construction, not just for 2D quantum field theories, but also to 1+1 dimensional spin chains. So let's take the simplest integrable model, the Heisenberg model, which is defined like this. And in the spin chain, what we want to do is to mimic the identification that we have made in the quantum field theory. So we want to identify sites which are at antipodal locations. Okay, so that's very easy to do. So at a given site J, you entangle the state at the site J with the state at the site J plus L over 2. Okay, and then you take the product over all states. Okay, so this is the way we define the crosscap state, and it's clear that the entanglement here is very long-ranged because you identify points which are across the spin chain. And this is very different from the case of the boundary states in the spin chain. So in the boundary states, typically the boundary states are defined locally, in the sense that you start with some at the site J, you entangle the site J with the site J plus 1. And then if you carefully choose these coefficients here, you get something which might be integrable. Okay, so here is just a plot of the, it's a trivial statement that the entanglement entropy as a function of the distance. In the case of the boundary state, it's always small. In the case of the crosscap, half of the system size. And this dashed line is just a general chaotic state. Okay. So importantly, one can show that, in fact, this crosscap state that we defined here is annihilated by infinitymetric conserved charges. And this is precisely the condition that defines integrable states in general. That was proposed by Zamolodchikov and then generalized to the lattice by these guys. Okay. So okay, so once we have this, we can then compute overlaps as before, exactly as a function of the S matrix of the model. But okay, this is very similar to what we have seen before, so I won't spend too much time. Let me just contrast this with the boundary overlap, which also has a similar structure, although it possesses also some non-universal factors. Okay, this is not very relevant, but what I want to highlight from this first part is the following. So the main outcome is that 2D integrable theories in a crosscap, they remain integrable. In closed spin chains, the integrable states, integrable crosscaps are obtained by identify antipodal sites. Okay, so that's the picture that one should keep in mind, because it also will play a role later in this talk. And once we have this integrable structure, we can compute exactly these crosscap states in terms of a basis of bulk states. Okay, so that's basically the summary of this first part of the talk. Okay, and if there's questions, this is probably a good time to ask. If not, I will move to 4 dimensions. Okay, so let's go to 4D. And as I promised in the beginning of the talk, the goal will be to study n equal to 4 super Yang-Mills theory, which is the maximally supersymmetric theory in 4D. And we're going to study it in RP4. And then I will mention something about the worldsheet crosscap. Okay, so let's now think in general and before specifying to n equal to 4. And let's start with a manifold, which is RPD in general D dimensions, although I will be specific of D equal to 4, but this is completely general. And let's put a CFT on this manifold, RPD. So as I said, RPD, you should think of like a D sphere where you identify antipodal points, but you can also project this into the plane by some stereographic projection. And in that case, the identification that you make is essentially inversion up to this minus sign. Okay, so now you can restrict yourself to a ball of size of radius 1, and then points outside the ball will be identified with points inside the ball. Now, generally, because of this identification, the Euclidean conformal group, which is SOD plus 1, 1, will be broken down to SOD plus 1. And that's very easy to see from this picture. So, for example, dilations are clearly broken just because they move points outside the ball. The symmetries that are preserved is a combination of the special conformal transformations and translations, and together with SOD rotations. Okay, and these two generators together, they form the SOD plus 1. Now, because the CFT, the conformal symmetry, strictly speaking, is broken, you now get new conformal data, namely the one-point functions of spinless operators. Okay, and now, as I've mentioned before, due to the fact this is a manifold that is locally conformally flat, it means that the local OP data remains the same. And how does this old data that we know from flat space and this new data that we get in RPD plays along together? Well, the relation between the two comes from this new bootstrap condition, which is just a very simple statement. So if I look at the 2-point function, as I bring 2 points together, O1 and O2, I have to remind myself that O2 actually has a mirror image by this inversion. And here, there's immediately something that has to be consistent. So the 2-point function in this channel will be equal to the 2-point function in the mirror channel. And now, if I expand the 2-point function in terms of the VEVs of these operators, then this will relate the VEVs with the structure constants and also conformal dimensions. So this is the way everything gets together. Now, let's be more specific about n equal to 4. So n equal to 4 super Yang-Mills is a theory that contains 32 supercharges, as it's well known. So 16 Poincare supercharges and 16 superconformal boosts. Now, under this antipodal map or inversion, Q's and S's are essentially exchanged. Poincare becomes superconformal boosts and vice versa. And so the best we can do, the maximum amount of supersymmetry that we can do, is to preserve Q plus S. And this halves the original number of 32 supercharges. So this is what's called a 1/2 PPS setup. 1/2 just comes from the fact that you have the amount of supercharges. And so this is it. So that's the symmetries that we have. Now, to fully specify the theory on this manifold, I need to tell you how the elementary fields are identified. And that's essentially fixed by the space-time symmetries, okay? So for example, let's take a scalar and consider like the sphere. So I have one scalar at one point, and then it will be identified with a scalar at the other point. And one can show that by this remnant superconformal symmetry, the identification holds up to a sign of ±1. Okay, so in fact, 3 out of the 6 scalars of n equal to 4, they do not pick up a sign, and the other 3 pick up a sign, which means that our symmetry, the SO6 R symmetry of n equal to 4, is broken down to SO3 times SO3. Okay, and the same, you can now work out also the transformations for gauge fields, for fermions, and that always follows from the space-time symmetries. But n equal to 4, in fact, has SUN gauge group. Okay, so we have to remind ourselves that these fields are actually in the adjoint of the gauge group. So they are expanded in terms of gauge group generators. So I can also try to make some transformation at the level of the gauge group transformations. So I can say that the generators at this point will be identified with the generators at that point without any change. But I can also do something which is what I mean by gauging the charge conjugation. Charge conjugation is, of course, a symmetry of the SU1 gauge group. It's, in fact, an outer automorphism that essentially conjugates the generators. So T goes to minus T star, which is essentially the transpose generator. So I can say that, in fact, I identify these two fields, but at the same time, I also change the gauge generators. And as we'll see, these two options lead to completely different theories. Okay. So let's see how it works. So let's consider the new observables 1-point functions at tree level. Let's do a simple exercise to see that these two different ways of putting the theory on RP4 will lead to very different theories. So let's consider a single trace operator at tree level. Okay, so a single trace operator is just a product of elementary fields, disjoint fields, and take a trace. So that's a gauge invariant operator. Now, if I don't do the charge conjugation, I have, this is how I represent in double line notation, a bunch of fields inside a trace. I have to use only the propagator in RP4, which is given by this. So here it's the scalar propagator. So it has two terms as opposed to the standard scalar propagator in flat space. So it has a new term that remains finite as x goes to y. And these red lines represent the way I contract the gauge indices. So with this propagator, the way I compute the 1-point functions is just by doing these contractions. And if I normalize it properly, I see that the 1-point function actually scales with n. Okay, that's a simple tree level exercise. But now, if I do the charge conjugation, now because the mirror image, the gauge generator is now transposed, the gauge propagator, or sorry, the scalar propagator gets modified. In particular, the indices of the gauge group gets modified. And in particular, this second term, the way you contract the indices is different. So if you now do the same computation as here, you will find that the configuration or the contraction that maximizes the number of faces, so the leading n contribution, is the one where you contract fields at opposite locations inside the trace. Okay, so you can do the exercise of using this propagator for example, for this type of contraction, and you'll find that this will be subleading. So this is the leading contribution, and it's of order 1 in a certain normalization. Okay, so I have, in one case, 1-point functions that scale with n, the other case, 1-point functions that scale with 1. Now, if we think in terms of holography, this is dramatic, as a dramatic effect. So n, according to holographic dictionary, gets mapped essentially to the inverse of the Newton's constant. And so this type of scaling suggests very much that the holographic dual, whatever it is, should be something that it's still asymptotic to ABS5 cross S5, which is the dual of n equal to 4 in flat space, just because the theory in the UV is not modified. But in order to have these large 1-point functions, you really should have something different in the bulk. Okay? And so this suggests that one should find a new classical Euclidean background, which is asymptotic to ABS. In this other setup, given that the 1-point functions are of order 1, what we'll find is that the background is still ABS5 cross S5, with what we will find a probe-orientifold O1 plane that extends inside the S5. And it's just a single probe orientifold, so it does not backreact, and so the geometry is not modified. And what is nice about this last setup is, as I will going to explain, it's integrable in the large n limit. Okay? Good. So let me first discuss holography for the case where we don't gauge the charge conjugation. So as I said, we should find a new Euclidean classical background in type 2b supergravity, which is still asymptotically APS and has this huge amount of isometries. So it's a half PPS background with these isometries. So SO5, which is the space-time symmetries, and then the SO3 times the SO3, which is the remnant of the R symmetry. Here I write SO2, 1 just because I'm in Euclidean signature, but that's an important detail. And I will, of course, not go into the details of this construction, but the strategy will be, instead of dealing directly with type 2b supergravity in 10 dimensions, I will apply what's by now a standard technique of constructing the solution in 5D in n equals 8 gauge supergravity and then uplift to 10D in type 2b. Okay. So technically, this is very similar to something that some people might be familiar, which is the Jano solution, which describes the interfaces in n equal to 4 with 16 supercharges. So technically, the exercise that we're going to do here will be very similar to what these two groups of people did, especially this last paper here of 2020. Let me, instead of spelling out the details of this construction, which is quite standard by now, let me just show the result. So we can find a new analytic Euclidean solution of type 2b supergravity. And just to flesh out the metric in 10 dimensions, this is how it looks like. So let's break this into pieces. So there is the 5D metric, which is of the warped form. So there is a slice which is RP4 here. And of course, the metric of RP4 is the same as 4. So there's no distinction at this point. And there is here some function that will be fixed. And then there are the parts of the metric that realize the isometries. And here there are some explicit functions of R. And this warp factor here, this exponential of 2a, is given explicitly by this as a function of R. Okay, so the details are not crucial, but I just want to point out a few facts. So first of all, the solution is a little bit more complicated than the standard ADS5, cross S5, because you have to turn on also a non-trivial dilaton, also Ramon and SNS2 forms, and also the 5-form flux. But what is nice about this theory or this solution is that it has exactly the boundary behavior that we expect. So these bulk fields, as we approach the boundary, they give rise to VEVs, but not sources, which means that the boundary theory is undeformed. The Lagrangian remains the same, which is what we expect, because the Lagrangian is something local, which is not modified in RP4. But at the same time, there's something here which is a bit funny, which is that we find actually a parametric family of backgrounds, not just a single background, but a parametric family of backgrounds parameterized by some constant j here. Okay, so as we take j to 0, we get back to the standard Euclidean ADS5 cross S5. But for j different from 0, we get something else. And in particular, this j is the one that controls the VEVs. So usually in this business of constructing supergravity solutions, one strategy to fix completely the solution is to demand that the solution becomes smooth or caps off somewhere in the IR. Okay, and that requirement of smoothness of the solution fixes a few constants. But here, what is somewhat puzzling is that we can actually show that the solution has a bulk singularity, in fact. Okay, so that's why we were not able to fix this constant j. Perhaps we might be able to fix it by comparison with gauge theory. But let me just briefly mention the problem. Well, it's not really a problem, but the fact that this fact that the solution has a singularity. So There is a point in the IR, some for fixed value of the radial coordinate and some fixed theta, where the metric actually has this form. So there is this factor h that goes to 0 as I approach the singularity. So it's, strictly speaking, it blows up close to this point. And the other fields have this behavior. The dilaton also blows up, and the C2 form also blows up. And the other forms close to the singularity, they go to 0. So this is a type of singularity that, in fact, is very familiar. And geometrically, in fact, it resembles Unorientable one plane in flat space. That's exactly the type of thing that you get in flat space for an Unorientable. But what is somewhat puzzling is that O-planes are incompatible with the previous large N counting. In fact, O-planes mean that you're gauging the worldsheet parity, and worldsheet parity on the string side corresponds to charge conjugation on the field theory side. But this is precisely the configuration where we're not gauging the charge conjugation. So although this geometrically looks like an Unorientable plane singularity, we believe that this is not really an Unorientable singularity. So, of course, the presence of the singularity might be worrisome, but in fact, I think there's no contradiction. And the way this usually works is that, well, the gauge theory has no singularity at all. It's perfectly smooth. So we would expect that a dual is also smooth. But maybe to find something that is smooth, you really have to uplift to the full string theory. So the expectation is that once you're able to uplift to the full string theory, perhaps alpha prime corrections will smooth out this geometry. But of course, this uplift is of course extremely hard to find, and we're not able to find yet. One idea is to try to use the gauge theory to see how this singularity is actually resolved. Okay, good. So let me now briefly mention two aspects of the other configuration where we gauge the charge conjugation. And what I want to say is the following. So basically the claim is that the one-point functions are given precisely by the cross-cap overlap that I spoke about in the first part of the talk. So the reason is twofold. On one side, as I will explain, the holographic dual involves a prob-orientifold. And orientifolds, what they do at the level of the worldsheet is to precisely introduce crosscap. So we know that the worldsheet theory of strings in ADS5 cross S5 in the large N, they are integrable. So I'm just saying that I have this 2D quantum field theory and then I'm adding a crosscap. But that's precisely the situation that we found before. And the claim was that this presence of crosscaps preserve integrability. Okay, so that's the worldsheet counterpart. But also in the gauge theory counterpart, there's a very cute story, which is the following. So if you're vaguely familiar with this story of integrability in N=4 super Yang-Mills, you would probably know that the way we think of single trace operators, so single trace are these products of adjoint fields taking the trace, we think of them as spin chain states, in fact. So the idea is that each field inside the trace you associate to a site on a spin chain. Here, if you just have two types of fields, you will have like spin down and spin up. But more generally, if you have more fields, it will be a more complicated spin chain. But that's the punchline, is that we think of gauge invariant operators as spin chains. Now, what we found before is that when we compute the one-point function, what we found is that the V contractions that survive in the large N, or the ones that are dominating, are the ones for which you contract fields which are at antipodal locations inside a trace. But that's exactly what spin chain crosscap state does, is to identify sites at the antipodal locations. So in other words, the gauge theory in the spin chain language is actually realizing the crosscap overlap or the crosscap state that I spoke about. Okay. And therefore, the claim now is that since we know the worldsheet S matrix of ADS5 cross S5, we can just apply the previous formula to compute the one-point functions. And so we can compute this one-point functions exactly in the 't Hooft coupling just by using the previous formula. Okay. So that's the result. And well, since I'm running out of time, I will skip. I had some comments about the holographic counterpart of n equal to 4. And let me.
Sorry,
yeah.
Can you say again, what's the spin chain antipodal conjunction?
Okay. So
example of the relation between this O operators maps to trace of the phi.
Okay. So the idea is the following. So the idea is the following. So in n equal to 4, we deal with single trace operators of this form here. Okay. So these are matrices. So formally, you can think of them as spin chain states, where like each site corresponds to an elementary field. That's just formally. Now, before I showed you how to compute these one-point functions at tree level by doing the V contractions of these fields. And I showed you that the leading large N contribution is the one where you contract fields inside this trace at antipodal locations here. So this is like a trace, you have the elementary fields, and the leading contribution is the one where you contract these fields with the one at antipodal location inside the trace. Now, if you translate that to the spin chain language, this means that you're entangling a site, the site J, with a site at J plus L over 2. Okay, but that's precisely what we found before, that the crosscap state does that for you. So when you overlap some spin chain state with a crosscap, the job of the crosscap is precisely to make this identification. And as we have seen, the crosscap state in the spin chain is integrable. So the claim is that this also preserves integrability. So of course, this is a tree-level statement. Now we turn on the 't Hooft coupling, and the question is whether this integrability is preserved, and that's certainly non-trivial. But we also have evidence of that from the worldsheet theory. So basically, we have evidence from integrability from both ends of the perturbation theory, like large 't Hooft coupling and small 't Hooft coupling. But perturbative checks, this is something that we are doing right now. But I think there's solid evidence that integrability will be preserved.
Okay. Thanks.
So let me skip this brief discussion for holographic n equals 4 with charge conjugation, and let me just mention some conclusions. So I showed you that crosscap states preserve integrability, and n equal to 4 is integrable in the planar limit if we gauge the charge conjugation when we place the theory on RP4. And also, in the case where we don't change the charge conjugation, we get some description of the model at strong coupling via some new Euclidean solution of type 2b supergravity. Right, so there are many things that I would like to discuss as an outlook, but perhaps let me just mention a few. So one is perhaps the second point where we found this new holographic background that contains singularities, which geometrically resemble the Orientable type singularities that we find in flat space. And one question is, how does the gauge theory help to resolve these singularities? So we have some sort of a definition, or like a definition of the full theory, like the CFT or the n equal to 4 on RP4 is perfectly well defined in the UV. So that's the real non-perturbative definition of the theory. So presumably that it would be interesting to see if there's something that we can use on the gauge theory to probe this type of singularities. Also, there is the fact that this second setup where we gauge the charge conjugation involves Orientifolds, and we can construct this Orientifold state or crosscap states on the worldsheet exactly. Is there anything that we can extract for more general for Orientifolds from its knowledge, explicit knowledge in this particular model? Yeah, so let me just stop here. I think that there will be interesting points to discuss, but perhaps this is taking too much. So thank you very much for the invitation, and feel free to ask questions.
Yeah, thank you very much. Thank you, João. Thank you for the talk. Question and comments from the audience. I guess you can take this time to say whatever you have now you have time to say if you want to.
Let me see. Right. So one of the things that perhaps I could say is one interesting thing is that in fact one can also study these models using what's called localization. So we can, in fact, compute exactly the partition function of n equal to 4 on RP4 without the charge conjugation. And that was shown by Yi Fan Wang, that you can reduce the theory to the Yang-Mills on RP2. So there are two things that one can do. So this allows us to also match things that we can compute on the supergravity side with things that we can compute on the gauge theory side for certain quantities, certain BPS quantities, and this is something that perhaps it's useful to study, because that allows us to, for example, fix this family of solutions that we found. So fix this additional parameter, but at the same time, it might also to do some sort of precision holography there. But perhaps more interesting is to see if there is some similar story for the case where we gauge the charge conjugation. The conjecture would be that by localizing n equal to 4 on RP4 with charge conjugation, you would reduce to the Yang-Mills on RP2 with also charge conjugation. And it would be interesting to construct these matrix models that describe this theory. So that's perhaps one comment of something that we are thinking. Yeah, I think that's one comment. Regarding the story of the crosscaps in 2D, Yeah, I honestly would like very much to know if one can use the crosscap to probe some property of the theory that perhaps it's harder to do it otherwise. But yeah, so far, it hasn't been totally clear of how to do it or what kind of questions we can ask to like what questions or could the crosscap answer? But maybe that's just a matter of thinking a little bit harder, which we haven't done.
By the way, Jean, I think you are aware that given a theory with the same symmetry, like time reversal, that you can put on unorientable manifold, and with possibly even the same local operators, they do can have a different class, different theories that they may have a different time reversal property exon lines and maybe extend operators.
Right.
So for example, even given Yang-Mills theory, SU2 and with or without theta terms, and you can consider with time reversal symmetry, and there's no charge conjugation for SU2, but that's fine. Just use time reversal, and you can actually tell that they are distinct class of such even the pure Yang-Mills. I think for the interest, people will study for some of the unorientable cases, the theta equal to pi. In that case, you can actually tell that actually they are at least 4 distinct class of Yang-Mills, such that the time reversal acts on the Wilson lines in a different way. Some of the Wilson line on the time reversal actually forms a doublet, like a Kramer's doublet, and some of them just Kramer's singlet. And another case is that when the Wilson line is open up, suppose at high energy you can somehow open up the Wilson line, then there is some way you can tell whether the endpoint attached is the bosonic or fermionic particle. And that suggests the way the Wilson lines as the 1D line operators can be probed by coupled to as a boundary of some 2-dimensional surface operator that allow the coupling of this W2 Stiefel-Winnie class. That means there's some property about the spin structure differ for the 2D surface probe. So in some sense, there are some Yang-Mills with different property on the Wilson lines, and even with the same time reversal symmetry, and one can distinguish them by computing the anomaly and put on unorientable manifolds. So in those story, do you see any, like even put on unorientable manifold, do you see distinct class of a series, and they could not be told only if you put on orientable manifold, but you could tell the difference if you put on unorientable manifold?
I see.
Are there some, because when you try to do, are there some
right.
Yeah, so the distinction here is that when you restrict to orientable manifold, maybe many class of theory looks the same.
Right.
But when you put on unorientable manifold, it looks different.
Right. Well, okay. There's one thing that it's kind of obvious, but say let's say in 4 dimensions. For example, when we study n equal to 4, we always set theta angle to 0. And of course, it's a little bit. I mean, we can set it to theta different from 0, but it doesn't play much of a role, at least, well, certainly in the large N, it doesn't play a role. But actually, it's expected that the theory on an orientable manifold in RP4 distinguishes theta equal to 0 and theta equal to pi, which those are the only two theta angles that you're allowed to turn on. And the expectation is that the theories will be distinctly different in that case. So, of course, putting the theories on unorientable manifolds makes them a little bit more sensitive to like global properties of the gauge group, for example, or theta angles, topological couplings. So yeah, I think there's basically anything you can think of. If you put an unorientable manifold and you turn on some topological couplings, things will be sharply distinct. And that's the example that comes to mind. N equal to 4 at theta equal to 0 or pi is expected to be very different. And in all my discussion, even in holography, I restricted the discussion to theta equal to 0. But it would be interesting to see what are the changes if you turn on theta, set it to theta equal to pi. It's expected to be very different. And in fact, we were not able to construct the holographic dual for theta equal to pi. But it's something, yeah, that's something that comes to mind. Yeah.
Mm-hmm. I think you know the example, like just consider so-called Kitov chain OR invariant into the dimension. If you only look into the spin manifold with Fermat parity, you can only tell the Z2 class, right? But if you include also with pin minus structure, there are 8 distinct classes. So the 8 compile to go to Z2, but you can tell A class. And this is not a CFT, but these are just some invertible TQFT. But am I correct that your talk or your work is not trying to address possible distinction, at least not yet, to distinct many class of theory that maybe looks the same on orientable manifold, but you can distinguish them on non-orientable manifold.
Right.
Not at least not yet, or some.
Yeah, not yet.
Okay.
We didn't try to address this question, but it's of course very, very interesting. I think one should think further about that.
Yeah. Okay, thank you very much.
Thank you.
Thank you. So I'll send you a recording. Thank you very much, Ron. It's very nice. Thank you.